So now I'm going to go over the analysis section of your IA. The analysis section is marked out of 6 points. The maximum of 6 points means that you have included sufficient, relevant, quantitative and qualitative raw data to support a detailed and valid conclusion. Appropriate and sufficient data processing is carried out accurately, and a conclusion is drawn which is consistent with the data. So what does that mean so far? That you have enough data to actually come up with a conclusion. This means that your range is big enough to firmly say that your hypothesis is correct. We'll come back to this when we actually look at some values in a minute. We also need a research question which is consistent. I've actually had reports in the past where the graph shows that A is proportional to B and the conclusion states that it's inversely proportional, right? Usually done in a rush or inaccurately. So be careful, always go back to your data and make sure you're stating a conclusion that's real, that you've got evidence for. The report shows evidence of full and appropriate consideration of the impact of uncertainty. So basically, if we have a look at the rubric, uncertainty is a very, very important part of this section. And uncertainty is in the 3 to 4 points. So the report shows evidence of some consideration of impact of measurement uncertainty. And then even here, even just to get 2 marks, the report shows evidence of little consideration of the impact. So if you don't do any assessment of uncertainty, the maximum score that you can get is 2 marks. Okay. The process data is correctly interpreted so that a completely valid and detailed conclusion to the research question can be deduced. Now, what do we mean by a valid and detailed conclusion? Well, that your conclusion involves uncertainty analysis, and so therefore you've got a range of possibilities. So, for example, in an experiment where you're trying to find G is equal to something, G is in the gravitational, the acceleration due to gravity, 9.81, where you state your final value. My value is G equals 10, but my uncertainty is plus or minus 0.5. The predicted value is 9.81, which falls within my range of uncertainty. That is a completely valid and detailed conclusion. To do this, to reach a valid conclusion, ultimately what we're looking for is a graph. This piece of work actually achieved a grade 7, and I'm really fussy now, so even I would have a few things to say about this graph now, but I'm going to use it to just give you a bit of an idea of what your final graph should look like. Your final graph should have a line which represents the trend. The points should have error bars, and then you need to have a positive and a negative maximum and minimum gradient, right? So lines representing the maximum and the minimum slope, and that would give you 3 equations in the end, 3 equations of the line, which would eventually lead you to your final conclusion. Now, in order to get that, you need tables, you need raw data tables. Now, your raw data tables must be presented very, very clearly, completely separate to the processed, and they must have consistent significant figures or decimal places, whichever's relevant at the time. So here we can see that all of these numbers have the same decimal places down the column, because they're using the same instrument. So in the columns, within the columns, you should have the same decimal places, and then do the same with all of your data. It should be consistent. Then you need a section which outlines your processes, which I think is over here. So here you can outline your data processing. So you've presented your nicely clear, set out and clear data. Here's your data processing, which is a description of everything that you're going to do to your data. And then you show the process data on the table. Now, what's really important is that whatever you do to the raw data, whatever you do to it, you must maintain the same number of significant figures. So here we can see that there is absolute uncertainty, or current average. Here we go. Your average current is showing 3 significant figures. Why have we chosen 3? Because the current that we had in the first place is 3 significant figures. So whatever you do to your raw data must end up then with the same amount of significant figures. Okay, so your first table is your raw data. Then you have a section on your processes, everything that you're going to do to your raw data. And then finally, you have your process data. And that leads you to your graph. Now, this graph now, I'm not entirely happy with, and I'll tell you why, so you can improve on it. I would like a graph which is much larger, if you have space for that. Nice large graphs, and the points, the plotted points, should be very, very small. They should not take up hardly any space. So use as small a dot size as you can, where you can still see it. So that's what I've got an issue with here. Apart from that, the rest of it seems fine. You can have a false origin, which is fine if that's helpful for you. And you make sure that you label your axes correctly, and you would use a key to show your maximum and minimum slopes. When you're stating your conclusion, the first thing you have to do is to go back to your research question. So let's go back and find our research question on this paper. Blah, blah, blah. See if we can find it. Here we go. My research question then is, how does the temperature affect the resistance of the copper wire? So now you go to your conclusion. The first thing you say in your conclusion, all the way down here, is, in conclusion, the change in temperature is proportional to the resistance of the copper wire. So they've stated their answer to the research question. The hypothesis was correct. Next point. Then you provide your evidence. If you can see in my graph, the equation for my line of best fit, which is it's difficult to tell because there's so many, it's the blue one. So if you see the line going close to the blue points, a bit of a ropey conclusion of this graph considering the size of the error bars, but here we can see the equation results in RT 0.418, that's the gradient, the slope of that line, plus or minus 0.007. So this candidate has worked out the maximum and minimum difference in the slope of the line. And they've shown that in their conclusion here. Now, what do we mean by working out the maximum and minimum slope? Well, they've got a result of 0.001, yet their maximum slope is 0.002, and their minimum is 0.001. So they've worked out the difference between those two. There is a slight variability, but you'd have to read the whole report to understand why it's a little bit different. But basically what we're looking at is some kind of processing here of the data, the result and the difference between the maximum and minimum gradient. Okay, I hope that makes sense. So now I refer to the checklist, which will help you make sure that you've got everything done. You need to make sure that when you're taking your data, you've got at least 3 trials. You've definitely stated how you kept the control variables constant. It's not just enough to say, I'm going to make sure that height is always the same. You actually have to say, I will make sure that height stays the same by marking the wall and holding up my object to the same point, avoiding parallax errors. Go crazy with it. Show that you really care about making sure that things are fair. Specific information on how errors would be avoided. So this would be in your method. How did you avoid all the errors? Not just mentioning the errors, but how to avoid them. And then you've given the uncertainty of your measurement. This is where it starts to get challenging. On your raw score table, you must state the uncertainty of the measurement, right? So if I go back to the piece of work here, what do we mean by that? This is the first type of uncertainty that you must show, the instrument uncertainty. So on your raw score table, you must have a measure of uncertainty for the instruments that you're using. Next, wrong one, got a lot of things open. You've taken sufficient data. Now this is to do with your range, that you've gone from the maximum and minimum value you could possibly have. So if you're looking at intensity of light with distance, that you've gone as close as you can to the light source, and as far away as you possibly can within the situation. If you're doing a pendulum, you've done a small one and a huge one. You've taken a good range. You've taken repeats. You've separated your raw data to your processed. You've used the correct number of significant figures. You've stated how to process your data methods. The number of significant figures of the processed data are correct, right? So I've mentioned that before. Your graph scales are labeled correctly. The size and scaling is appropriate. And as I said before, try and make your graph a page if you can, and ensure that the plotted points take up more than half the axes. What do I mean by that? Well, let's have a look here at this graph. Oops, going the wrong way. The plotted points here, they take up most of the graph space. Sometimes, especially if you don't use a false origin and you need one, what you've got is the plotted points in one tiny area of the graph and the rest of it is blank. You want to avoid that. Okay, you should be able to see your points taking up most of the document. You've worked out your gradient, super important, and you can just use the liner best fit function on your sheets, on Google Sheets or Excel. Now you've worked out the uncertainty of your raw scores and the uncertainty of the processed data. So that's a little bit of processing that you have to do, either in terms of the averages, you have to work out the uncertainty of the average, or other calculations which would depend on what you're actually investigating. I'll deal with that one-to-one. That you've done your error bars and your maximum and minimum gradient are found. So this is what you definitely need to have for your results and analysis. And although I've already spoken about conclusion, the conclusion section would come into evaluation, and I'll talk about that next.